You think dark matter is something I never touched. A modern discovery, right? Something found decades after my death by astronomers peering into distant galaxies with instruments I never lived to see. Wrong. I didn't just predict dark matter. I discovered the exact mechanism that makes it necessary, wrote down the mathematics that demand its existence, and then walked away from it because what I found was so unsettling that even I couldn't fully accept what my own equations were screaming at me. In 1939, 15 years before anyone pointed a telescope at a galaxy and noticed something was catastrophically wrong with our understanding of gravity, I published a paper that contained the blueprint. And here's the thing that'll bend your morning in half. The number at the heart of my calculation was 3. Just 3 solar masses. That's the threshold where matter stops behaving like matter and starts doing something else entirely. So here's the question that will chase us through everything that follows. What happens to reality itself when you compress mass past the point where my equations say space should rip? Let me put you somewhere concrete. Imagine you're floating in the darkness between galaxies, millions of light years from the nearest star. You're watching a cluster of galaxies, hundreds of them, swirling around each other like a slow-motion hurricane made of light. You clock their speeds. You measure how fast those galaxies are orbiting their common center. And when you run the numbers, checking how much gravitational pull you'd need to keep them bound together at those speeds, you find something impossible. The mass you can see, all those billions of stars glowing in every galaxy, accounts for maybe 15% of the gravity you're measuring. The other 85%, it's there. You can measure its pull. You can map where it sits. But it's invisible, completely dark. That's the story you've been told about dark matter, and it's accurate as far as it goes. But it's not where the story begins. The story begins in 1950, the moment I finished general relativity. I'd just rewritten gravity not as a force, but as curvature. Mass bends space, curved space tells mass how to move, and the whole dance is encoded in equations so beautiful that physicists still get chills reading them for the first time. But I immediately noticed something strange lurking inside my own creation. When you take my field equations and push them to an extreme, when you ask what happens if you compress enough mass into a small enough volume, the math doesn't just bend, it breaks. Space curves so violently that it folds in on itself. Time slows, stops, then ceases to mean anything recognizable. And at the center, my equations predict a boundary, a point of no return, a place where, if you fall past it, not even light can climb back out. I hated it, called it a monstrosity. The term black hole wouldn't be coined for another 3 decades, but I spent years trying to prove that nature had some built-in safety mechanism, some rule that would prevent this collapse from ever actually happening. And that's when I wrote the 1939 paper. I modeled a rotating cluster of particles, worked through the mathematics of how tightly you could pack them under their own gravity, and found my threshold, roughly 3 solar masses, compressed into a tight enough orbit, and the system becomes unstable. It either flies apart or it collapses into something my equations described, but my intuition rejected. I concluded in that paper that such objects probably don't exist in nature. I was wrong about that. You've now photographed the shadows they cast. But here's the twist. Nobody tells you about that paper. In proving to myself that black holes couldn't form, I accidentally derived the exact conditions under which matter becomes gravitationally dominant over light. I found the regime where mass that doesn't shine, mass that doesn't interact with photons, still exerts its full gravitational weight on everything around it. I described dark matter's signature, and I did it before anyone knew galaxies were rotating too fast. The mechanism was already there, sitting in my equations, waiting. You're probably wondering why this didn't make headlines in 1939. Why didn't I connect the dots myself? The answer is simpler than you'd think, and it's going to reshape how you understand what equations can and cannot tell us about the universe. I had the map, but the territory hadn't been explored yet. The observations that would reveal dark matter's presence were still 15 years away, and I'd be gone before they arrived. I had the key, but nobody knew there was a lock, and the reason that matters, the reason we're spending the next several minutes inside this idea, is that the mechanism I found doesn't just explain dark matter. It predicts that dark matter and visible matter can't be separated. They're locked together by the same geometry, which means the universe you're living in right now is fundamentally different from the one you think you see when you look up at the night sky. So if I had the mechanism in 1939, and the observations confirming something was missing didn't arrive until the 1950s and 60s, what exactly were those astronomers seeing that made them realize the universe had a hidden skeleton? And more importantly, why did it take another 20 years after that before anyone thought to look back at my old paper and notice I'd already described the trap? The first person to actually see the problem wasn't looking for it. Her name was Vera Rubin, and in the 1970s she was doing something that sounds almost boring until you realize what it revealed. She was measuring how fast stars orbit inside spiral galaxies. Simple rotation curves. You point your telescope at a galaxy, you measure the speed of stars at different distances from the center, and you plot it. Standard astronomy, textbook stuff. Except when she did it, the textbook ripped itself apart. Here's what should have happened. Imagine you're on a merry-go-round. The farther you stand from the center, the faster you're moving through space, even though the whole platform rotates at the same rate. But if you're a planet orbiting a star, the rules flip. The farther out you are, the slower you should orbit, because there's less mass inside your orbit pulling on you. Mercury screams around the sun every 88 days. Neptune takes 164 years. That's gravity working exactly as I predicted. The visible mass concentrated at the center determines the speeds everywhere else. So when Rubin measured stars at the outer edges of galaxies, way out past most of the visible matter, she expected to see them crawling along, lazy and slow. They weren't. They were screaming. Stars at the outer rim were moving just as fast as stars closer in, sometimes faster. And that meant one of two things. Either my equations were wrong at galactic scales, or there was mass out there that nobody could see. Mass that didn't glow. Mass that formed a massive halo around every galaxy, extending far beyond the visible stars, holding everything together with invisible hands. The numbers were obscene. For every kilogram of stars and gas you could see through a telescope, there had to be 5 or 6 kilograms of something else. Something dark. Now here's where it gets strange. When I wrote my 1939 paper, I wasn't thinking about galaxies at all. I was thinking about stars, compact objects. I was trying to prove that nature wouldn't allow mass to collapse into those monstrosities my equations predicted. But the mathematics I used, the conditions I derived, they didn't care about scale. The mechanism I described works the same whether you're talking about 3 solar masses in a tight cluster or 3 trillion solar masses spread across a galaxy. The principle is identical. Once you have enough mass in a given volume of space, the curvature becomes self-reinforcing. Gravity doesn't just pull on matter, it pulls on itself, and that creates a regime where dark, non-interacting mass can dominate the gravitational field without emitting a single photon. I never saw Rubin's data. I died in 1955, 2 decades before she published her rotation curves. But if I had seen them, I would have recognized the signature immediately. This wasn't a failure of my equations. It was a confirmation. The universe was showing exactly the behavior my mathematics demanded when you push mass and curvature into the regime I'd mapped out and then dismissed as unphysical. Let me give you the moment that makes this concrete. Picture Rubin in her observatory. It's sometime in 1976, and she's just plotted the rotation curve for Andromeda. She's staring at a graph that should slope downward, and instead it's flat. Stubbornly, impossibly flat. The stars at the edge are orbiting at 200 kilometers per second when they should be limping along at maybe 70. Her first thought isn't dark matter. Her first thought is that her equipment is broken. She checks the spectrograph. She recalibrates. She measures again. Same result. She tries another galaxy. Same problem. Another. Same. It's not the equipment, it's the universe. And here's the sound I want you to hear. The click of her pen as she draws the inevitable conclusion on her notepad. Not a dramatic moment, just a click. But that click is the sound of a door opening into a room I'd built in 1939 and never walked into. Because here's what Rubin couldn't have known while she was sketching out the mass distribution that would explain her curves. The geometry she was inferring, this massive dark halo holding galaxies together, it matched precisely the kind of gravitational structure my equations generate when you have mass, in the regime where space-time curvature becomes non-linear. She was observing from the outside what I had derived from the inside. Two completely different approaches, 4 decades apart, converging on the same hidden architecture. But nobody connected them, not right away. Rubin's discovery was treated as an observational mystery. Astronomers started cataloging dark matter, mapping it, measuring it. They gave it a name, built models, argued about what particles it might be made of. Cold dark matter, warm dark matter, axions, WIMPs, sterile neutrinos. The physics community threw itself into the search for the particle, the thing, the stuff that was causing all this excess gravity. And in all that searching, all that model building, almost nobody stopped to ask whether I'd already described the mechanism that makes dark matter inevitable. You want to know why? Because my 1939 paper wasn't about dark matter. It was about black holes, and I'd concluded they probably didn't exist. So the paper got filed away as a historical curiosity. Einstein trying to save the universe from his own equations. A dead end. Except it wasn't a dead end. It was a roadmap. And the road led directly to the invisible scaffolding holding your galaxy together right now. Here's the part that should make your skin prickle. The mathematics I wrote down doesn't just allow for dark matter. It requires it. Once you accept that my field equations correctly describe gravity, once you accept that mass curves space-time and curved space-time governs motion, then dark matter isn't a mysterious add-on. It's a prediction. The equations are telling you that in any sufficiently massive system, there must be gravitational influence that exceeds what you'd calculate from visible mass alone. The geometry demands it. And I saw that demand in 1939. Work through the numbers, and then convince myself nature wouldn't go there. Nature went there. Your living inside the place, I said, was impossible. Now here's the part nobody tells you, the part that flips the entire story inside out. Everything I've just described, Rubin's observations, my equations, the dark matter halos, all of it is still just the surface, because there's a deeper layer to this mechanism, something buried in the way my equations treat mass and energy. And when you pull that thread, the whole picture of what dark matter actually is starts to unravel in a way that's both more elegant and more disturbing than anyone expected. Now, here's the part nobody tells you. Dark matter isn't missing. You are. Let me explain what I mean by that, because it's going to flip everything you just heard inside out. When physicists talk about dark matter, they frame it as the mystery, the invisible stuff. The 85% of the universe's mass that we can't see. But that framing hides something profound. My equations don't distinguish between dark and visible matter. To general relativity, mass is mass. A kilogram of hydrogen and a kilogram of dark matter curve space-time identically. They're equivalent. So the real question isn't why is there so much dark matter? The real question is why is there any visible matter at all? Think about what visibility actually means. For you to see something, it has to interact with light. Electrons have to absorb photons and re-emit them. Atoms have to scatter electromagnetic radiation. That's not the default state of matter. That's a special case. That requires matter to carry electric charge, to couple to the electromagnetic field, to play by a very specific set of rules that only a tiny fraction of possible particles actually follow. Most ways of having mass don't involve any of that. Most ways of being real don't require glowing. So here's the reframe. The universe isn't mostly dark matter with a little bit of visible stuff sprinkled in. The universe is mostly normal, and you're the exotic anomaly. You're made of the weird matter. The matter that happens to interact with photons. The matter that's chatty enough to light up and announce its presence. Dark matter is just matter doing what matter does by default. Existing, having mass, curving space-time, and not bothering to wave hello. And I predicted this, not explicitly. Not in those words, but the mechanism is right there in the field equations I published in 1915. When you write down how energy and momentum curve space-time, there's no requirement that the energy be electromagnetic. There's no clause that says only things that glow count. The stress-energy tensor, the mathematical object that describes the source of gravity, it accepts all forms of mass and energy on equal terms. Visible, invisible, kinetic, potential. It's all the same to the curvature of space. The equations are colorblind. They don't care if you shine. Let me take you back to 1939, to the specific calculation I did that year. I was modeling a cluster of particles held together by gravity, trying to find the point where the system would collapse into one of those monstrosities. And here's the detail that matters. Nowhere in that calculation did I specify that the particles had to be atoms. I didn't require them to have charge. I didn't assume they interacted with anything except space-time itself. I was working with pure gravitational dynamics, mass points, generic matter. And what I found was that you could pack these particles into a stable rotating cluster up to a certain threshold, roughly 3 solar masses in a tight configuration. And beyond that, the geometry becomes unstable. But here's what I missed. What I couldn't have seen without Rubin's data. That same mathematics, scaled up, describes the dark matter halos around galaxies. The stable configuration I was calculating, it's not just a curiosity about compact objects. It's the generic solution for how matter arranges itself under gravity when it's not being pushed around by electromagnetic forces. Stars and gas, the visible matter, they're subject to radiation pressure, magnetic fields, all these electromagnetic interactions that stir them up and distribute them in complicated ways. But dark matter doesn't feel any of that. It only feels gravity. So it settles into the pure gravitational equilibrium that my equations describe. The halo isn't mysterious. It's matter behaving exactly as my mathematics predicts when you remove all the electromagnetic complications. You're starting to see it now, aren't you? The mechanism isn't something separate from general relativity. It is general relativity operating in its cleanest form on matter that only does gravity and nothing else. Now let me show you where this gets truly strange. In the decades after Rubin's discovery, astronomers mapped dark matter halos around hundreds of galaxies, and they found something unexpected. The halos aren't random. They have structure. They follow profiles, mathematical distributions that describe how the density changes with distance from the center. And the profile that shows up most often, the one that fits the data best, is called an NFW profile, named after the 3 physicists who characterized it in the 1990s. It's a specific curve, a specific relationship between radius and density. Here's the thing that should make you stop breathing for a second. When you take my field equations, assume only gravity is acting, and solve for the equilibrium distribution of matter in a rotating system, you get that profile. Not exactly, the full calculation is messier, but to a first approximation, the shape is there. Mathematics I wrote in 1915 predicts the structure of dark matter halos observed in 1995. 80 years apart. I gave you the equation, nature showed you the solution, and it took most of a century for anyone to notice they matched. But there's a deeper layer still, and this is where the mechanism reveals something about the fabric of reality that even I find unsettling. The equations allow for something I never anticipated. They allow for mass without local presence. Let me unpack that phrase, because it's going to sound like nonsense at first. In Newtonian gravity, mass is a thing. It's here, or it's there. It has a location. You can point to it. But in general relativity, what we call mass is really a property of the space-time curvature in a region. The curvature can be smooth, distributed, smeared out in ways that don't correspond to little billiard balls sitting at specific points. And when you solve the field equations for systems dominated by gravity alone, you find solutions where the mass isn't localized. It's woven into the geometry itself. This is the part where I have to be careful because the mathematics here gets slippery, and the clean version requires tools we don't have time for. But roughly speaking, dark matter might not be particles in the way you think of particles. It might be a feature of space-time geometry, a kind of persistent curvature that carries energy and momentum and therefore acts as a source of gravity, but doesn't correspond to little bits of stuff you could ever isolate or detect directly. My equations allow for this. They practically invite it. And if that's what dark matter is, if it's geometric rather than particular, then the reason we haven't found the dark matter particle, despite decades of searching, is simple. We're looking for the wrong kind of thing. Now I need to pump the brakes for a moment and give you the honest version. This geometric interpretation of dark matter, it's not mainstream. Most physicists still think dark matter is a particle, something like a neutrino, but heavier and more standoffish, and they might be right. The data doesn't rule that out, but what the data does show, what Rubin's curves and every observation since has confirmed, is that dark matter behaves exactly like my equations say pure gravitational matter should behave. And whether that's because it's a particle that only does gravity, or because it's geometry pretending to be mass, the mechanism is the same. The mechanism I found in 1939. Here's the sound I want you to carry with you from this section. The hum of space-time itself, vibrating with curvature, holding galaxies together not with invisible ropes, but with the shape of reality. Not a click this time, a hum, constant, everywhere, inaudible, but foundational. So if I'd already described the mechanism by 1939, and if that mechanism explains everything we've observed about dark matter since, then why does the question still feel unsettled? Why are physicists still building detectors deep underground, still smashing particles together, still searching? Because there's one piece of this that even my equations can't answer. One question that separates a mechanism from a complete understanding. And it's the question that ties everything we've talked about back to that opening moment when I stared at my field equations and realized they predicted something I didn't want to believe. So here's what we can do and what we can't. We can predict exactly how much dark matter should be in your galaxy. We can map where it sits, how it's distributed, how it holds the stars in their orbits. We can run the mathematics forward and backward, plug in the mass of the Milky Way, and calculate the rotation curve to within a few percent. The equations work. They work stunningly well. My field equations, the ones I published in 1915, describe dark matter's gravitational effects with the same precision they describe Mercury's orbit or the bending of starlight around the sun. We can predict it. What we can't do, what even I couldn't do, is tell you why the universe chose this particular ratio. Why 85% dark and 15% visible? Why not 50-50? Why not 99-1? The mechanism explains how dark matter behaves once it's there. It doesn't explain why it's there in the amounts we observe. And that gap, that unanswered why, it's the same gap I faced in 1939 when I tried to prove black holes couldn't exist. I had the mathematics. I could describe exactly what would happen if enough mass collapsed into a small enough space. But I couldn't tell you why nature would or wouldn't allow it. I made a guess based on intuition, and I was wrong. Nature had no problem with black holes. She makes them constantly. So when modern physicists look at dark matter and ask what is it made of, they're really asking my question from 1939. Not does the mathematics allow this, because it clearly does, but what does nature actually build when she uses this mechanism? And that's not a question equations can answer. Equations tell you what's possible, what's consistent, what's allowed. Observations tell you what's real. Let me take you back to that image from the beginning. You're floating in the darkness between galaxies, watching that cluster of galaxies swirl, measuring the gravity that holds them together. You found that 85% of the mass is invisible. Now you know that's not a mystery. That's my equations doing exactly what they're supposed to do. Mass curves space. Curved space governs motion. The mass doesn't have to glow to curve space. It just has to be there, The mathematics I gave you in 1950 guaranteed that if enough mass gathered in one place, most of it wouldn't need to interact with light to dominate the gravitational field. The halos, the rotation curves, the missing mass, it's all matter obeying the cleanest, simplest form of gravity. Pure geometry, no electromagnetic clutter. But here's what that image was really showing you. The thing you couldn't see while you were busy counting up the gravity. You weren't looking at a normal cluster with some dark matter added. You were looking at dark matter's universe with a thin film of visible matter floating on top. The stuff you can see, the stars, the galaxies, the glowing gas, all of it is cosmetic. It's the paint job on a car you can't see. The real structure, the chassis, the frame, the engine, that's all dark. The visible universe is the exhaust, and I built the blueprint for that chassis in 1915 without realizing what I was drawing. Remember the threshold I found? 3 solar masses in a tight rotating cluster, the point where the system tips from stable to collapse. That wasn't just about black holes. That was the first glimpse of the regime where gravity stops being a weak background effect and becomes the dominant force shaping matter's behavior. Scale that regime up to galaxies and galaxy clusters, and you get halos. You get dark matter. You get the invisible skeleton that keeps the cosmos from flying apart. The threshold wasn't a warning, it was an invitation, and the universe accepted. Here's the part that still unsettles me. Even now, when I finished general relativity, I thought I was describing how matter tells space-time how to curve. But the equations are symmetric. They also describe how space-time curvature tells matter where to be. And in that second reading, dark matter isn't stuff that happens to be there. It's the equilibrium state that curved space-time naturally generates. The geometry creates the mass distribution, and the mass distribution creates the geometry, and the whole thing locks into a self-consistent configuration that my equations describe but don't explain. It's a loop with no beginning, a structure that exists because it can, not because something built it. We can predict it, map it, measure it, and model it. We can't tell you why it chose to be. Now let me give you the 2 lines you won't be able to unhear. Dark matter isn't the universe's secret. Visible matter is. You're not living in a cosmos with something missing. You're living in a dark matter universe with something extra. Something bright and loud and electromagnetic. Something that glows just enough to let you see how much you can't see. And here's the honest piece. The place where even my equations reach their limit. I can tell you the mechanism. I can show you the geometry. I can prove that the mathematics demands exactly what you observe, but I can't tell you what dark matter is made of, why it exists in the proportions it does, or whether it's particles or pure curvature or something we don't have words for yet. The equations give you the how. Reality owes you nothing about the why. Remember that click you heard, Rubens' pen on the notepad, the moment the door opened? Here's what was on the other side. Not a new particle or a new force. Just my equations, waiting patiently in a room I'd walked past for 24 years, describing a universe where most of reality doesn't bother to shine, where gravity writes the story and light just adds footnotes. Where the invisible isn't hidden, it's foundational. I gave you the theory in 1915. I gave you the mechanism in 1939. I just didn't tell you what you were looking at. But that's how physics works. The equations arrive first. Understanding limps along decades later, and sometimes the person who writes the equations down is the last one to believe what they say. You think you live in a universe of stars and light, with some dark matter sprinkled in the gaps. No, you live in a dark matter cosmos that happened to sparkle in a few places. And every time you look up at the night sky, you're seeing the exception, not the rule. The visible stars are the glitter on an invisible ocean. And I charted that ocean before anyone knew it was there. That's not a mystery. That's gravity doing what I told you it would do. You just weren't ready to hear it.